So let's see what we are getting here. We are getting of u and v is not part of the edges of the GF of delta, right? That basically means that if we look at the residual graph, right, then that basically means that C of E minus F of E has to be less than delta. If C of E and minus F of E, if this is not true, right, then you sort of see that C of E minus FE is greater than or equal to delta. In this case, the edge moving from U to V survives after we delete all the edges whose capacity is delta, right? So this is different from the conclusion we get, right? So that's the reason that we have to have that the C of E minus F of E less than delta. And after having that, right, so we can sort of get back to the terms over here, right? So I'm going to sum up, what I was doing is that sum up all of E out of A, F of E. Then I also know that C of E is minus F of E is less than delta, right? So this implies F of E is This implies, let me just erase a little bit. This implies C of E is less than or equal to F of E plus delta, right? And then using this relationship, we have we can get this term E out of A and C of E minus delta, right? So this is why we get this kind of inequalities. So let's switch back to the slides and see how this is going to help us to. Now we are getting back this busy slide. So let's erase what we have again, right? So now what we stop at was we want to prove that the first line is greater than or equal to the second line. All right. Just now we show that C of E is going to be less than or equal to F of E plus delta, right? So this implies F of E is going to be greater than or equal to C of E minus delta, right? So this is implying the if I look at each of the component, F of E is greater than or equal to C of E minus delta, right? We can use a similar argument to prove the second term also has this kind of component-wise relationship and establish the first inequality, right? This is how we get the first inequality, right? So this is really just at a very high level. This is the properties of the capacity scaling algorithm, right? Now from here to here, let's see what we are doing here. Right? So we are really just breaking up the terms. I don't think this is inequality. This is equality, right? So I put all this term together. It really just becomes E out of A, C of E, right? So now I put all this term together. The term of this two term together, it goes to this term, right? So E out of A delta, and this term would be the same as this term, right? So this is an exact equality, right? So after we have this exact equality, right? So now we sort of know that E out of A basically is really just the capacity of A and B, right? So now I'm sort of summing up of E out of A and summing up E into A, right? But all this, we can sort of consolidate this, right? So this is the sum of E out of A or E inside A, right? And delta. But the total number of edges is really just M, right? So no matter how much we sum up, right, we can just give a conservative bound of M, right? M is really just the number of edges, right? And that's the reason that we also have the third inequality is at least as the capacity of the A and B minus M times delta. So let me just clean up everything and really just go back to the very high level idea of all the deviations here, right? The first one would be the flow value lemma. The second one would really just be the property of the capacity scaling algorithm, and exactly more specifically by the way how we delete edges, right? The third one are just the moving around the terms, right? The fourth one is using the fact that if I sum up all the E's, it won't be larger than the total number of edges, right? So it's really just solely just that all E are smaller than the number of edges here. Right. So with all this, then we managed to establish that value of F is at least as large as the capacity of A and B minus M times delta. right? And then capacity of A and B is at least as large of value of the optimum solution minus m times delta, right? This is the weak duality. After all this, then we managed to show the lemma 2. Right? So after we show the lemma 2 and together with the argument we have for the lemma 3, then we managed to prove the entire theorem. So the entire theorem, if you just repeat, right, I do encourage you to read through this multiple times. It's really chaining up multiple smaller components. Each of the components is not that complicated. It's really just that it's one of the longer proof that you have to chain up multiple components, right? So in case you are interested in doing the algorithm research, right, this kind of argument is actually not very complicated. You need to be able to get used to the fact that sometimes when you need to prove the correctness of an algorithm or the running time of an algorithm, you do need to chain up the different type of observations here and there and put them together, right? So now, by now, we sort of wrap up the entire capacity scaling algorithm. We managed to show its running time of the algorithm. It is the running time of this algorithm. It's polynomial in the size of the network, right? So now, up to this moment, then we wrap up the entire max flow mean curve analysis and as well as the flow algorithm, right? So we start. So let's just review what we have done, right? So let's see, right? So this would be the outline, right? So all the gray parts are what we have done, right? So we actually have achieved quite a lot. We are not going to deal with the rest of them, right? So we start with the introducing the max flow mean curve problem, and we quickly come up with a solution that's sort of based on greedy algorithm, right? So the greedy algorithm almost work, except that we really have to consider the residual graph more carefully instead of really just by just look at the original graph, modification of the original graph, right? So the idea is that if there's an A and B, the capacity is 10. I already used the 7 unit, right? Using the original gradient algorithm, we maybe just put 3 units of flow here, but in fact, we do need to allow us to regret to put the 7 unit of flow in the residual graph, right? So basically, after we introduce the notion of the residual graph, then we are able to really come up with a correct algorithm for finding the maximum flow. But in order to prove the correctness of the maximum flow, we do need to use the max flow mean curve theorems, right? So we also spend one lecture to prove the max flow mean curve theorem. But even the algorithm is correct, we sort of realize that the algorithm could be slow because we do have this kind of very funny instances, right? So this is 100. This is 100, this is 1, this is 100, this is also 100, right? So with this kind of funny instances, despite the fact eventually our algorithm will terminate and give you an optimum solution, it's going to be very slow. Then for today's lecture, we have been talking about how we can use the capacity scaling algorithm it's really just a modification of the original the focusing algorithm by being smarter in terms of choosing the augmenting passes, right? So we come up with this algorithm. This algorithm itself is pretty intuitive, but in order to prove its running time and its correctness, it's a bit involved, right? So at the end, I thought I just need the 30 minutes to go through everything, but maybe now it's already over 80 minutes. So we will just stop here today, and for the next 4 lectures, we're going to wrap up and talk about the NP-hard and intractability results. And again, thank you for watching the video, and see you